Hey everyone, this is the Space Channel. In 1974, the renowned theoretical physicist Stephen Hawking predicted a fascinating, though still unconfirmed, property of black holes, that they can actually emit particles. Just imagine it. A black hole, which rips through space-time and devours everything in its path, can release tiny particles. What could that possibly mean? You may have heard the well-known explanation involving particle-antiparticle pairs that form right at the event horizon and immediately annihilate. One of them can fall into the black hole, while the other escapes as radiation. As the black hole keeps swallowing antiparticles, it gradually loses mass and eventually evaporates. Well, it all sounds logical and even understandable, but is it really so? Or is it just a thought experiment? So let's try to figure it out. What exactly does a black hole emit? How long do black holes actually live? What is Hawking radiation really? And what is the Unruh effect? Let's dive in and explore this together. To be honest, all these relativistic and quantum effects we'll talk about today are much easier to explain through mathematics. But we're not here to give a lecture on mathematical analysis or quantum field theory. Instead, we'll try to explain everything as simply as possible, while keeping it detailed and accurate. You probably recall from school the excellent concept known as the theory of relativity. Most people didn't really like it because of its strange paradoxes and the weird effects it predicts. Of course, I doubt many of you have encountered those effects directly, like Lorentz contraction or time dilation. But on cosmic scales, it turns out you simply can't ignore them. The special theory of relativity is most often used to study various inertial reference frames and the effects and paradoxes that occur within them. Let's recall, inertial reference frames are those that either remain at rest or move uniformly, that is, at a constant velocity, relative to other frames of reference. The general theory of relativity, on the other hand, is used to study the phenomenon of gravity. That's why general relativity usually deals with curved spacetime, while special relativity works with flat spacetime, such as Minkowski space. However, it's pretty rare to find interesting relativistic problems involving non-inertial reference frames within special relativity. For example, uniformly accelerated motion must be described in a non-inertial frame of reference, and yet, the spacetime of that frame still turns out to be flat, which means it can still be analyzed using special relativity. Let's draw the world line of such a uniformly accelerated object on a spacetime diagram. Don't worry, it's not as scary as it sounds. We'll draw two axes. One represents time, and the other represents one of the three spatial dimensions. We won't draw all three since that would make it a four-dimensional diagram. On this diagram, light travels at a 45-degree angle, like this, and this line is called a null geodesic, or a light world line. Accordingly, lines that go straight up show an object standing still in space but moving through time. Lines that tilt slightly represent objects moving through both space and time at a constant speed less than the speed of light, and a line steeper than the light line would represent motion faster than light. Simple enough. Now, this particular world line has the shape of a hyperbola, showing that the object's velocity increases steadily over time, meaning the object is moving with constant acceleration. From this diagram, we can conclude that there exist light signals that an observer on such a uniformly accelerated object will never be able to see. All those signals lie beyond this boundary line, known as the Rindler horizon. The spacetime formed by all the world lines of uniformly accelerated observers who share the same Rindler horizon is known as the Rindler metric. Now let's move on to quantum field theory. It turns out that a uniformly accelerated observer near the Rindler horizon will actually see radiation. This is known as the Unruh effect, named after William Unruh. We won't dive into overly complex mathematics. Instead, let's use a thought experiment to make the Unruh effect easier to understand. Imagine we have two systems, one uniformly accelerated system with its observer and another, an inertial, non-accelerating system. The accelerated observer, even in a perfect vacuum with no external sources of heat, will detect particles and feel thermal radiation. Meanwhile, the inertial observer, at the exact same point in space, will see nothing at all. The reason is that the vacuum isn't truly empty. In quantum field theory, the vacuum is viewed as a collection of quantum fields existing in their lowest possible energy states. The energy states of quantum fields are determined by the Hamiltonian, meaning the total energy of the system, which includes the time component of spacetime. According to the special theory of relativity, time flows differently in different reference frames. As a result, observers in different frames perceive different energy states and therefore different vacua. This difference in energy states leads, from the viewpoint of a uniformly accelerated observer, to the appearance of a thermal bath. The thermal radiation observed by such an accelerated observer can be described by the spectrum of a perfect black body, with a temperature that depends on the observer's acceleration. However, this thermal radiation is extremely weak. For example, to detect radiation with a temperature of around 1 Kelvin, an observer would need to experience a proper acceleration on the order of 10 to the 20th meters per second squared. You might now be wondering, where does Hawking radiation and black holes come into play here? It turns out that there's a strong parallel and even a direct connection between the Unruh effect and Hawking radiation. Both of these quantum effects arise from differences in vacuum states, and their mathematical derivations are similar in nature. Moreover, the formula for Unruh temperature is actually used to calculate Hawking radiation. The radiation spectra of both effects are the same as that of a perfect black body. These similarities suggest that these two effects are manifestations of the same underlying phenomenon. According to the equivalence principle of general relativity, acceleration and gravity are equivalent. This is supported by the fact that the Schwarzschild metric, which describes black holes, is very similar to the Rindler metric, which describes uniform acceleration. Even a black hole's event horizon can be viewed as an analog of the Rindler horizon. From this, it follows that there must be radiation emerging near the event horizon, with a temperature that can be calculated using the Unruh formula. But here's the question. What kind of acceleration should we substitute into that formula? In the Unruh effect, acceleration referred to the observer's own proper acceleration. So what should we use in the case of a black hole? In this case, we should substitute the acceleration of an observer who remains at a fixed position infinitely close to the event horizon, but does not rotate. To maintain that position, the observer must constantly accelerate with an acceleration equal to 1 divided by 4 times the mass of the black hole. This acceleration corresponds to what an observer would experience under Newtonian gravity on the surface of a spherical body whose radius equals the Schwarzschild radius and whose mass equals that of the black hole. That's why this acceleration is often called surface gravity. By substituting this acceleration into the Unruh effect formula, we obtain the Hawking radiation temperature. Interestingly, an observer freely falling into a black hole would not detect any radiation at all. In my view, this explanation, though somewhat more complex, is actually more precise and closer to the physical truth than the usual description involving particle-antiparticle pairs. Some of the particles from this thermal bath are not absorbed by the black hole, but instead become outgoing radiation. And when something escapes from a black hole, it causes the black hole to lose part of its energy. And according to Einstein's famous equation, that means the black hole also loses mass. That's how it evaporates. The time it takes for a black hole to completely evaporate depends on its mass. For a black hole with a mass equal to that of the Sun, This time is almost impossible to even compare with anything. It's unimaginably long. Roughly 10 to the 67th power years, far exceeding the current age of the universe. Of course, for black holes with smaller masses, the evaporation time is much shorter. It's possible that in the early universe, there existed tiny primordial black holes with very low masses that have already evaporated. Or perhaps a few are still finishing their final moments now, and we might soon detect one. But for now, that remains unknown. If you enjoyed this video, please like and subscribe to the channel. See you next time.